Welcome to the explainer. You ever have that perfect set of data, everything's lining up, except for that one single point you actually need? Well, today we're going to look at a super powerful tool for filling in that blank, especially when it's right near the end of your data. Let's get into it.
So here's our roadmap. First, we'll lay out the problem. Then we'll introduce our tool for the job. That's backward interpolation. After that, we're going to unpack the formula behind it, piece by piece. Then we'll actually put it to work with a real example, and finally, we'll do a quick reality check on just how accurate this thing is.
All right, first things first. Let's really get a solid grip on the specific challenge we're trying to solve here, the problem of that missing point. Just imagine this for a second. You're tracking something, right? It could be anything, population growth, maybe stock prices, or data from some science experiment. You've got all your readings at these nice regular intervals. But what happens when the exact moment you care about falls between your last two readings? How do you make a really good, intelligent guess? This table makes our problem totally clear. We've got our data points here, and in this case, they come from the function f of x equals x cubed. But what if we need to know the value for 7.5? It's not on our list. But it's super close to the end of our known data. So the big question is, how do we figure out that missing value with some real precision? And that, of course, brings us to the solution. We need the right tool for this very specific kind of job, and that tool is called backward interpolation. But first, let's back up just a little. What's interpolation in general? Well, you can think of it as a really smart way of connecting the dots. When you have a series of known points, and they're all spaced out evenly, interpolation gives you a solid mathematical way to estimate what's happening in the gaps between those points. But here's the thing. Not all interpolation methods are created equal. You might use something called forward interpolation if your missing point was at the beginning of the list, like, say, 1.5. But for our problem, because our target of 7.5 is right at the tail end of our data, Gregory's backward interpolation is literally designed for this exact scenario. It works by looking back from that last known point. So how does this actually work? Well, it's time to pop the hood and take a look at the engine that drives this whole process, the formula itself. Okay, I know what you're thinking. This looks a little intense. We've got all kinds of symbols, factorials, but trust me, the idea behind this is actually really intuitive. What this formula is doing is building a special function, a polynomial, that perfectly weaves its way through all our known data points. We're going to break down exactly how it builds that model step by step. The logic here is actually pretty elegant. You start with the last known value, that's your base guess, then the formula just systematically adds a series of corrections. Each new piece you add on is a smaller, more refined adjustment that inches you closer and closer to the real value. It's kind of like fine-tuning a really sensitive instrument. And that's the million-dollar question, right? The formula is great, but it's built on these correction values. They're represented by that upside-down triangle symbol, which is called navla. In this case, it stands for the backward difference operator. I know, it sounds super technical, but it's really just a name for the values that measure how our data is changing. So where do they come from? They come from this thing right here, a backward difference table. And I know it might look a little complicated, but it's literally built on simple subtraction. That's it. You take a value, you subtract the one right above it, and you write the answer in the next column over. See? 512 minus 343 gets you 169. Then 169 minus 127 gets you 42. You just keep doing that. This simple process gives us all the correction values we need, 169, 42, and 6, that we're going to plug right into our formula. All right, enough with the theory. This is where the magic happens. We've got the problem, we've got the formula, and we've got our difference table. So let's put it all together and actually solve for f of 7.5. So here are all the pieces of our puzzle. Our target, x, is 7.5. The very last data point we have, xn, is 8. The step size between each point, h, is just 1. And from that difference table we just made, we can pull out those crucial correction values that line up with our last point, 169, 42, and 6. Now, there's just one more little piece we have to calculate. It's this variable called u. And all u really does is tell us how far our target point is from the last known point, but as a fraction of the step size. We just plug in our numbers, 7.5 minus 8, all divided by 1. And that gives us a u value of negative 0.5. Simple as that. And now, for the main event. We plug every single one of those pieces into the big formula. We start with 512. The first correction uses our u value and that first difference, 169. The second correction uses u again and the next difference, 42, and so on. See, that abstract formula has just become a straightforward calculation. And when you run the numbers, you get this, 421.875. Now in this case, because our original data came from a perfect cubic function, our interpolation gives us the exact answer. But what happens in the real world? We got a perfect answer that time, but that kind of begs a really important question, doesn't it? How accurate is this method when you're out in the real world and you don't actually know the function underneath it all?
Well, the short answer is no. Our example worked out perfectly because our data points came from a simple polynomial, a cubic function, and the formula is literally designed to recreate polynomials perfectly. But real-world data is almost always messier. So you have to think of this method as a powerful approximation, not some kind of magic wand. So what affects the accuracy? It really boils down to three main things. First, how curvy or complex the real function is. Smoother, simpler functions are just way easier to approximate. Second is the spacing between your data points. The closer your points are to each other, the better your estimate is going to be. And third, it's about where your target point is. The closer you are to a known data point, the less error you're likely to have. This quote really just nails it. What we're doing, essentially, is creating a polynomial that fits our known data points like a glove, and then we're using that polynomial to guess the values in between. The error, then, is just the difference between our polynomial guess and whatever the true function is actually doing. So remember, this is way more than just a math exercise. This core idea of looking back from your most recent data to predict a nearby point has massive applications. Think about forecasting trends, or smoothing out computer animation, or filling in missing gaps from sensor data. It's a fundamental tool for making intelligent guesses when you don't have all the information. So the question is, where could you use it?